Hi folks at home, can I just test that this is actually working? I can see Dan Shepherd's there. Dan, can you just take yourself off mute and say hello to me?
Hello?
Can you
hear me?
You can hear me then, Dan?
Yeah, I can hear you.
Perfect, thanks very much. So this is Chris, I'm one of the chemistry teachers. I'm just going to wait till a few more people have joined. I think we had nearly 50 people wanting to do this and we got to about 22 so far. Let's just wait till a few more have joined and then I'll get started. So hopefully, again, maybe Dan could just confirm. At the moment, I should be projecting something that's like the front cover of Optical Isomers and Carbonyls review. Is that what you're seeing at home, Dan?
Yep.
Excellent, good. Right, let's just see how many people we've got. Well, that's 24. If they're late, they're late. I'm going to get started. Right, so welcome everyone. We're just going to have a look at some questions that sort of quite regularly come up in the area of carbonyls. Carbonyls in this context actually means aldehydes and ketones. And before we actually get into the questions, I just thought it would be useful to remind ourselves what we're talking about when we talk about aldehydes and ketones. So you should be able to see in this slide. Oh, and by the way, Stuart Strathdee, another of the chemistry teachers, is sitting in another classroom. So if anyone does have any specific questions about what we're doing, Stuart's acting in a secretarial capacity this afternoon. He's been promoted, and Stuart's going to answer any of the questions that you'll send through the chat. So don't ask questions by unmuting. If you do have any questions, just type them in the chat area and Stuart will endeavour to answer them. So thanks, Stuart. So let's have a think about aldehydes and ketones. Clearly, aldehydes and ketones do have some things in common, yet they have significant differences. And I thought it would be useful just to spell out some of these similarities and differences before we start on the questions. So you'll see in this slide that actually both aldehydes and ketones have a carbonyl bond, C double bond O, and that carbonyl bond is polar. Both the molecules, or both this family of compounds, have that feature. So you'll see that we have a slightly positive carbon in the carbonyl, which we write delta plus above, and we have a slightly negative oxygen, which we write delta minus above. And that really gives us an indication into the sort of chemistry that carbonyl compounds will actually participate in. So that delta plus carbon in the carbonyl will readily attract nucleophiles. So the most common reaction that we're going to see with this type of substance is actually a nucleophilic addition. So what are the differences? Well, attached to the carbonyl group in an aldehyde, we have a hydrogen and we have a variable alkyl group, which I've just written as R. The main difference between the aldehyde and the ketone is that the ketone does not have a hydrogen attached to the carbonyl. So in a ketone, there are two variable alkyl groups attached to a carbonyl group, one either side. Now those two R groups, which I've labelled as R1 and R2, can be the same as each other, which you'd see in propanone, where R1 and R2 would both be methyl groups, or they can be different. So for instance, in butanone, where R1 would be methyl and R2 would be ethyl. The fact that an aldehyde has a hydrogen attached to the carbonyl group gives it slightly different reactivity to a ketone. So frequently, and there isn't an example in these questions, but frequently you might be asked for a test tube test to differentiate between an aldehyde and a ketone. The most common answer would be to use Tollens reagent, which gives a silver mirror with aldehydes, but not with ketones. But actually, and those of you who are in biology will also have met these tests, you could also use blue Benedict's or failing solution, and again, both of those will give a brick red precipitate with an aldehyde and not a ketone. So it is possible to tell aldehydes and ketones apart in a test tube test. Okay, bit of background. So now we're going to move on and have a look at the questions that I sent to you. So, first one. What we have here is an aldehyde with 1, 2, 3, 4, 5 carbons. So that aldehyde will be pentanal. We're going to do a reaction of that molecule with potassium cyanide, followed by dilute acid. That's actually equivalent to adding HCN, but we do it in 2 steps. And there's a question at the end that really thinks about why we do it in 2 steps. So this reaction gives us a racemic mixture of a hydroxynitrile, which is actually shown here. So, like a lot of exam questions, this one starts off gently. It's asking us for the UPAC name. So the UPAC name isn't any old name, and I know if I teach you, I like to go on about the old names that people have for these compounds as well. But the UPAC name is the Systematic International Union of Pure and Applied Chemistry name, which is the same everywhere on the planet. And we have to be careful here when we're naming this compound. It would be very easy to say, well, let's count the carbons. 1, 2, 3, 4, 5. Oh yeah, of course, the name's going to be based on pentane nitrile. But actually, people tend to forget that there is a carbon in the CN of the nitrile. So let's just highlight that and remind ourselves that actually, including that carbon, I've got 1, 2, 3, 4, 5, 6 carbons in this now. Reactions of aldehydes with potassium cyanide will actually add another carbon to the carbon chain. So this compound is going to be based on hexane nitrile. Now you might say, why hasn't he put a number with hexane nitrile? You don't need to. By default, the nitrile group is going to be at the end of the longest chain, and that is carbon number 1. But there's something that we haven't actually included in the name yet. So let's not forget about that OH group. So that OH group is actually attached to carbon number 2. So to give this its full UPAC name, we have 2-hydroxy hexane nitrile. Okay, so let's say we've done the reaction. Describe how you would distinguish between separate samples of the 2 stereoisomers of 2-hydroxyhexane nitrile. Now remember, in 2-hydroxyhexane nitrile, there will be a carbon, it's carbon number 2, that's got 4 different substituents. So that is a chiral carbon, this one here. How would we distinguish between separate samples of both of these? Well, what we need to do is shine plain polarized light through those 2 separate samples. And if we do shine plain polarized light through these 2 samples, we find that one of them can rotate the plane of that light in one direction, and the other will rotate it in the other direction by the same amount. So what we would say is that the enantiomers rotate the plane polarized light equally in opposite directions. And I noticed in this pack of questions that I just found on the system, there are one or two questions in this pack that have basically the same question. Now, moving on. What we need to think about next is why this reaction actually produces a racemic mixture. Notice the words here, racemic mixture. There are two alternative ways of saying this. Racemic mixture is one of them, the other one is racemate. Quite often, people tend to blend racemic and mixture together to make a word which I'm going to write here but then rub out. That doesn't exist as a word, racemics. It's a great word, very useful for playing Scrabble, but unfortunately gets you no marks in chemistry. So we'll forget about that one. So why do we get a racemic mixture? Why do we get a 50-50 mixture of both possible optical isomers? And really, to help us think about that, I've drawn a little diagram on the next page. So, all I've drawn there is the business end of the aldehyde. So that R group in the compound that we're looking at in this question would be a butyl group. But that butyl group plays no part whatsoever in the reaction, and it could be any alkyl substituent. Now, in this reaction, we've got a nucleophile, in this case, a cyanide ion, which has a lone pair on carbon as well as a negative charge. And that lone pair on carbon can attack the delta plus carbon of the carbonyl, which is slightly electron deficient, either from above. Now remember, if we have two single bonded substituents attached to a carbonyl bond, there are only 3 bonds there, and that environment is planar. So there's an equal probability of the nucleophile, the cyanide, attacking the carbonyl group, which is planar, from above or below. If you get attacked from above, you'll get one of the optical isomers. If you get attacked from below, you still get something that's chemically identical, but it will be the other optical isomer. Chance of either happening, 50-50. And that explains why you get a racemic mixture. So let's put that into words. So, first things first. In these questions where you have to explain things, it isn't actually necessary to write everything in lots of long sentences. In fact, my suggestion is that you keep things brief. You can even bullet point your answers. So in this case, we've got a planar carbonyl group. That planar carbonyl group can be attacked by a nucleophile from above or below, or from either side. And the probability of that happening from either above or below is equal. So with equal probability. You can see that this question is a 3-mark question. So 1, 2, 3. You write a one-word answer for a 3-mark question, it's very unlikely that you're going to get 3 marks. So there we're looking for the planar environment of the carbonyl group, the fact you can get attack from above and below by the nucleophile, and that attack happens with equal probability, or we produce equal amounts of the 2 isomers. Right, so that's the first question. Let's move on. So again, we've got something similar. Have we got the same one? Yes, we have. Right, coming back again. This one's now about an isomer of pentanal. So there's pentanal. This one's also going to do that reaction with KCN followed by dilute acid. And this time we get a product that doesn't show stereoisomerism. It doesn't produce a racemic mixture. It just produces one product which is not optically active. So what we need to do is think about the structure of that compound and why it doesn't show stereoisomerism. So in this question, really, the first thing we need to do is think about isomers of pentanal. So on the next page, I've actually drawn some. Now, I'll highlight all the aldehyde isomers. So here's pentanal itself. You can also have a 4-carbon aldehyde, a butanal, and that butanal could have methyl groups at the 2 or the 3 position. There's another one that I haven't drawn, I've just thought of. So you could have 1, 2, 3. Also have that one, dimethyl propanal. But unfortunately, all reactions of aldehydes with nucleophiles produce a carbon with 4 different substituents. They have to. You've got an alkyl chain, you've got an oxygen in an OH group that's produced in the nucleophilic addition reaction, you've got a hydrogen, and you've got the nucleophile is. The only exception to that is in methanal, which has 2 hydrogens either side of the carbonyl group, but that's not the case here. So what we need to do is actually have a bit of a wider think about this. And in fact, the isomer that we're thinking about is not even an aldehyde. What we need to do is think about ketones. So we need to be remembering that aldehydes and ketones are isomeric. So they're functional group isomers. And again, I've actually drawn some examples down here, so let's highlight them in a different colour. So we've got 2 isomers of pentanone, pentan 2-one and pentan 3-one, and we've got methyl butanone. Now, when we think about those compounds, the ketones, which I've highlighted in green, 2 of them will actually produce optically active products. So let's just mark the ones that produce optically active products. So this one will, and that one will. If you do the reaction with KCN, you'll end up in both those molecules with a chiral carbon. The only one where you don't is the one where the ketone is symmetrical, and that is pentan 3-one. pentan-3-one has two ethyl groups either side of a central carbonyl. So if you do a nucleophilic at that carbonyl group, then the product you get will not have 4 different substituents. It will only have 3. So if we go back to the previous page, let's have a look. Draw the structure of the compound formed. So I'm going to start with let's just draw that backwards. So we've got 2 ethyl groups either side of the carbonyl, or you might want to draw it in skeletal form, like that. And that's going to react with KCN followed by dilute acid to form this compound. So we've got an OH, we've got a CN on either side, we've got ethyl groups. You can see that there are only 3 different substituents on that central carbon. So some of you might have drawn it as a skeletal, in which case we might have this. So that's how you draw the skeletal. 1 mark for the structure. What's the justification? Simple. It doesn't contain a chiral center. So actually, there are many ways of actually saying that. It doesn't have different substituents on a carbon, or it's a symmetrical product. So there are different ways to get that second mark. Okay, let's move on. So now we've got a different molecule. Here we've got compound E, which is formed by the reaction of benzene with an electrophile. So most of you will have been doing this reaction probably this week if you're in. So this is formed by a Friedel-Crafts acylation of benzene. And compound E, it says here, it reacts with HCN to form 2 isomers. Really what we're doing here is a reaction with KCN, then dilute acid. Name and outline a mechanism for that reaction. So what we need to do is actually draw the molecule out. I think I'll draw it like this. So just so I don't have to draw that backwards, I'll just bend that propyl group back round that way. So let's draw the dipole in. Always recommend drawing that, even if it's not absolutely necessary. And we're going to do a reaction of this with a cyanidine. So we've got C, triple bond in with a lone pair, actually, and a negative charge on carbon. So I've drawn that sideways. We normally draw it around like that, but it's the same thing. So we'll draw a curly arrow. Really important where you draw curly arrows. They need to start somewhere specific and they need to finish somewhere specific. So in this case, we're going to start between the lone pair on the carbon, and we're going to finish on that delta plus carbon of the carbonyl. That will give us an intermediate. And that intermediate will have an O minus with benzene ring, propyl group, and the cyanide, which I'm now going to have to draw like that. It's actually straight, so I've just drawn it like that to avoid drawing NC backwards. That's an intermediate, which then needs to react with an H plus ion from dilute acid. Again, we need a curly arrow, and we will form there's our benzene ring, slightly wonky. There's our OH. We've got a propyl down here. And we've still got our cyanide over there. Now notice that we've got a chiral carbon. So let's just highlight that. This carbon is chiral. It's got 4 different substituents. We've got the benzene ring, a phenyl group. We've got OH. We've got propyl, and we've got a cyanide. So we need to say the name of that reaction as well. So this reaction is nucleophilic addition. Effectively, we've added HCN across that carbonyl bond. We've added an H at the oxygen end, we've added the CN at the other end. But we actually do it using KCN followed by dilute acid. And we don't need to do the next question because we've already done one like that. We've already suggested how separate examples of the 2 isomers can be distinguished. So that's the one with they rotate plane polarized light in opposite directions equally. Right. So let's have a look at this one. In this reaction, which is an example of, guess what? Nucleophilic addition. We need to draw our aldehyde. So this time, the aldehyde is propanol. Let's draw the cyanide the right way around. So we've got a negative charge on carbon, a lone pair. Let's draw the dipole. So the carbon in that carbonyl is electron poor, electron deficient, and we're going to attack it with the lone pair on the cyanide ion. So that cyanide ion comes from HCN. And I'm missing another arrow. So nitrile, H there, ethyl group up there, and this then would accept a proton, giving a hydroxynitrile. And again, we can see that we've got a racemic mixture here because we've got a carbon that has 4 different substituents. So that's a chiral carbon. Now, actually, it's interesting that this question actually says the reaction with HCN is very slow, and there's a very good reason for that, which I think we're going to have a look at in a minute. Usually when you do this reaction, you use potassium or sodium cyanide followed by dilute acid. The overall effect is the same, it's equivalent to adding HCN, but that reaction is very slow. So, what do we need to do next? Draw some enantiomers. Well, okay, this is where we have to think in 3 dimensions. Someone once asked me, what's the hardest thing about going from GCSE to A level? And I genuinely think it's starting to think in 3 dimensions. Before that, you haven't really thought about chemistry as being 3-dimensional, but actually it is very 3-dimensional, and it's really, really important in nature and medicine. So in this one, we've got a central carbon. It doesn't matter which way round you draw the substituent the first time you draw one of these. So I'll just go with what I've got on the screen. So I've got an ethyl group up there. I've got a hydrogen down here, and then I'll have a cyanide up in a wedge bond, and the OH down in a dashed bond. There's the mirror. Let's have a look at the other one. So again, there's no need to reflect that substituent. It can just stay looking exactly the same. Coming down to carbon, I've got a hydrogen over here this time. Again, I've got a cyanide sticking up. I'll just draw that backwards just to show that it is like that. And here's where we have to be careful as well, because it would be very tempting to write OH here the same way around as the other isomer. But here we have to show that it's actually oxygen that's bonded to carbon. So we do definitely need to write that OH the other way around. So there we have the 2 enantiomers, both in equal amount. So actually, though we have got 2 optical isomers here, because they're present in exactly the same amount, then there's no overall effect to plane polarized light. Okay. Let's move on. How could we distinguish between the 2 isomers? We've already done it. And you see these sort of questions come up again and again and again and again. So they'll rotate plane polarized light equally in opposite directions. So you can say it in one sentence and get both of the marks. Let's just go back and have a look at the structure of that compound so we can name it. So, now again, when we're naming nitriles, we have to be careful that we include the carbon of the nitrile itself. So in this case, if we do a count of carbons, we start at the nitrile carbon. We've got 1, 2, 3, 4. So this is going to be butane nitrile, and The only other substituent that we haven't considered yet is the OH on carbon number 2. This one. So we've got 2-hydroxy. So this is simply 2-hydroxy butane nitrile. No numbers needed for the nitrile. The assumption is that's carbon number 1. And finally, there's this question. Now, someone that I teach actually asked me about this. You've been doing all about Kc and Kp recently. So you've recapped Kc. You've done all this stuff about the other equilibrium constant we need to know about called Kp. This one's Ka, and we'll meet that when we look at acid dissociation. So I thought it would be useful to just actually write an expression for Ka. So for any weak acid like hydrogen cyanide, we can write an expression to show this. So this is hydrogen cyanide forming H+ ions and Cn- ions. Just like any other equilibrium constant, when we're looking at concentrations, Ka is the concentration of the protons multiplied by the cyanide ions divided by the concentration of the undissociated acid. And really, given your knowledge of K, as in Kc, you should have been able to predict with this question that if Ka is a very small number, what that means is the top line of this expression must be very small, and the bottom line must be very large. In other words, this equilibrium must lie very much towards HCN, so that there is hardly any H+ or Cn- in this reaction, which explains why it's very slow. So, how do we explain this? We can say the value of Ka is very small, therefore the HCN to H+ plus Cn- equilibrium must lie to the left. In other words, the concentration of Cn- ions is very low. And therefore the reaction is very slow. So that's quite an interesting question. Notice how it started off with being an organic question, and it actually gets you into thinking about physical chemistry. Now, I realise the acids and bases topic hasn't actually cropped up yet, but based on what you already know about equilibria, I thought it would be useful to actually keep that question in there. So it's one of the key facets of chemistry at A level, is that topics from physical chemistry might appear in a question on organic chemistry. So it's all sort of interwoven. So really, you need to learn things not in boxes. You need to be able to link all those boxes together in your mind. Good. Were there any more questions? Let's have a look. Oh yeah, one more. Right, last one. Butanone is reduced in a two-step reaction using sodium borohydride followed by dilute hydrochloric acid. Write an overall equation for the reduction of butanone using H to represent the reductant. So what we're starting with here is butanone. So if we react butanone, here it is, we need to react it with some moles of, we're just going to write H, and what we'll produce when we reduce an aldehyde or a ketone, what we get is an alcohol. So in this case, we'll get CH3, CH2, CH, OH, CH3. So we've gone from butanone to butan to 1. Now, that is not a balanced equation yet. So if we look carefully, we see that butanone has 8 hydrogens, and our product has 10. So to balance, we need 2 H's. Now at A level, we do this reaction as a nucleophilic addition, and we write a mechanism for this one using as nucleophile H-. So sodium borohydride is a source of H- ions. So it is quite common to see people trying to write reaction mechanisms involving BH4s, but actually we don't actually do that at A level. We just use H- as the nucleophile. Remember, that's a hydrogen with an extra electron, so it's got a lone pair. So final one, the questions that we all hate as chemists, 6th mark level of response questions. So by considering the mechanism of the reaction, explain why the product has no effect on plane polarized light. Well, if we look at this molecule, if we look at the second carbon in from the right, we'll see that that is in fact a chiral carbon. So this one, there's an ethyl group, a methyl group, an H and an OH. So that is a chiral carbon. So why does this product have no effect on plane polarized light? So what we're going to do is actually spin something that we've already done before into the right format for a level of response question. So all of these level of response questions will actually fit into 3 stages. In this one, let's consider stage 1 first. So stage 1 actually is all about the nucleophile attacking the planar carbonyl group from either side. So I'm going to do this in 2 ways. I'm going to do it in words first. So we can say the H- nucleophile can attack the planar carbonyl group from either side. Now you could illustrate that with a picture and still get the marks. But if you cover nucleophilic attack, let's do a bit of highlighting. There's nucleophilic attack on a planar carbonyl group and that attack can happen from either side. An H minus. Then we've covered everything in stage 1 in one very brief, not even a sentence. So if we do all of that, all of stage 1 and nothing else, then that'll be 2 marks out of 6. Level 1, 2 marks. Let's have a look at stage 2. So, on the mark scheme, by the way, stage 1 is about forming the product. Stage 2 is about the nature of the product. What is the product like? So, I think we need to show what the product actually is. So here we could actually draw it. So there we are. We've got butan 2-ol. So if we draw a picture, it could be skeletal, or it could be drawn like I drew previously. All of those are acceptable ways of drawing butan 2-ol. And we'll have to say that it exists as 2 enantiomers, which are formed in equal amounts. So if we do all of that, if we say what the product is and the fact that it exists as 2 enantiomers formed in equal amounts, we've clocked up all the marks for stage 2. We could draw the optical isomers here. So another alternative would be to simply this one. There's the other. So if we drew them and we wrote that they were present in equal amounts, that would also clock up the marking points for stage 2. And the final stage is to talk about optical activity. And we've all been able to repeat this. It's like a bit of a mantra of chemistry. So the optical isomers rotate plane polarized light equally in opposite directions. That doesn't quite get you all the marks of stage 3 though, because what we need to say is why this product doesn't rotate plane polarized light. And the reason for that is with a racemic mixture, the effect cancel. So actually there's no rotation of plane polarized light. One isomer rotates one way, the other rotates it the other way, and the effect cancels out. So if we do all those things, we get a nice level 3, 6 marks, and keep the examiner happy. Good. That's what everything that I propose to say about aldehydes and ketones. I hope you've managed to send Stuart some questions if you have any questions on the way through. I hope I haven't made any mistakes. I'm sure Stuart will come and tell me if I have. So have a good afternoon and stay safe. There'll be another of these coming next week. Thank you very much.